The final big concept is the law of gravitation. Let me just quickly repeat that because you might already know that any two masses will attract each other with a force which will be proportional to the product of those masses, and which will be inversely proportional to the square of the distance between them, right? So the force of attraction between any two mass m1 and m2 will be directly proportional to multiplication of m1 and m2, and that force will be inversely proportional to the square of the distance between them, or in other words, that force will be directly proportional to 1 over r square, right? So when you combine these two proportionalities, you get an equation which is the Newton's law of gravitation, where capital G is the constant of proportionality. It is called as the constant of gravitation. It is a universal constant, and its value has been determined using several experiments, sophisticated experiments, and now we know exactly its value. Let's quickly work out the units of this capital G. G will be actually, according to Newton's law of gravitation, will be F times R square over m1, m2, right? So let's now use that expression to work out the units of capital G. First do it for example, System International, and then we can repeat it for the US customary units. In System International, the units of G will become, force will be in Newton, R will be the distance between two masses, so it will be meters, so it will be meter square, and then two masses will be in kilograms, so they will be kilogram square because both will be in kilogram, right? So G has the units of Newton meter square per kilogram square in the System International. But we also know that in System International, force is a derived quantity which can be written in terms of the other three basic quantities. So Newton can be written in terms of kilogram, meter, and second. So let's now replace in the same system, let's replace Newton with, because Newton is equal to kilogram meter per second square, using F is equal to ma. So let's replace Newton with that, kilogram meter per second square multiplied by meter square, and that whole thing is divided by kilogram square, right? Everyone is clear on that? So I simply replace Newton with kg meter per second square in SI system, and let's cancel out 1 kg with that, and second square will come down, and the final units will be meter cube over second square times kg, right? Everyone is clear with that? How I came up with these units? So these will be the units of capital G in SI system, right? So it is 6.673 into 10 raised to power minus 11 meter cube divided by kg into second square, right? So now you know exactly how these complex units we have seen in SI system. In US customary, the same G will have a different value and also will have a different unit also, because of the same difference that mass is considered derived quantity in US, but force is considered a derived quantity in System International. So in US units, let's derive the units of this capital G, again using the same expression, F R square over m1 m2. So force will be in US units, force will be in pounds, R will be in feet, so it will be feet square, right, divided by m1 m2, and mass is in sludge in US units, so it will be sludge square, right? So pound feet square divided by sludge square. But now again we know that sludge can be written in terms of other three base units, and let's quickly do that. We know that F is equal to ma, so mass is equal to force divided by acceleration, and force in US unit is in pound, acceleration is in feet per second square, so second square will go up, right? So pound second square per feet. that is equal to 1 sludge. Let's put that here. So we will be having pound feet square divided by sludge square, and sludge will become pound second square divided by feet, and then whole square of that, right? So this whole thing which I am now encircling will become the units of capital G in terms of base units for in US unit system, right? So we can simplify it further also, and we will get this quantity. We will see that 1 pound will actually cancel out with 1 pound because it is square. Similarly, feet also will go up. It will become feet 4 because feet also have a square on that. So there will be a feet raised to power 4 on numerator divided by the 1 pound which will left into second raised to power 4. There is also one difference in SI versus US units, that generally in US units there is a small dash to actually separate two different symbols in a big unit. So it's not pound minus second raised to power 4, it is pound times second raised to power 4, right? But in SI units we simply use a dot to actually separate two different unit symbols. So everyone is clear how we come up with this very complex unit in US customary system? Feet raised to power 4 divided by pound into second raised to power 4. One interesting thing is that these units, like, they cannot be related one to one. For example, you have that the length raised to power 3 on top, but here you have length raised to power 4 in US system. Similarly, you have kilogram second square. Here you have pound second raised to power 4. So there is no like one-to-one correspondence between these derived units in these two unit systems. Now let's discuss the effect of two important phenomena on gravity. We now know that the force of gravity is defined by this equation. All we need to know is to determine the mass of two objects and the distance between them, and then we are good to go to calculate the gravitational force, right? But in case of Earth, there are two phenomena which affect this force, and we may need to correct our calculations to account for those phenomena. One is a direct phenomena, and that is that our distance from Earth's center may not remain same. A person who is standing on the surface will have a different small r value, but a person out there somewhere in space will have a different distance, and therefore will feel a different force of gravity, right? And second phenomena is the effect of rotation of Earth. The rotation of Earth, or the very fact that we are also revolving, rotating with it, actually modifies the force of attraction which we feel on the surface of Earth. So the last topic in this chapter would actually be the effect of altitude on gravity, and then second will be the effect of rotation of Earth on gravity. So rotation of Earth on gravity. But first let's discuss the effect of altitude. We know that if, for example, there is an object resting on the surface of Earth having a mass m, it will have the distance from the center of Earth, where all the Earth's mass can be assumed concentrated for the purpose of calculations. The distance between them will be equal to the radius of Earth itself, right? So if I write, for example, force of attraction between Earth and that mass which is resting on its surface, that should be simply equal to capital G, mass of Earth, multiplied by that mass on the surface, divided by the radius of Earth square, right? Using the Newton's gravitational law. But that force which that object will be feeling, the attraction of Earth, is actually its weight, right? So that weight can be mass times the gravitational acceleration, and that can be equated to gme multiplied by mass of that object divided by capital R square, where capital R is the radius of Earth. M can be cancelled out, and we have G equal to capital GME over R square. Capital G is a gravitational constant, Mass of Earth is known, it's a fixed constant quantity, and same is the radius of Earth, it is known, it is a fixed constant quantity, right? So we can calculate the value of small g, which is the gravitational acceleration or acceleration due to gravity. We can calculate using that expression. But that expression actually is uh, valid for an object which is resting on the surface of Earth, right? So that is equal to capital G mass of Earth divided by r square. So this G actually is on the surface, not somewhere out there in the space. Let's call that G as G naught, right? Now let's change the case and assume that you are now, that mass is located somewhere at a height equal to small h, let's say like this, and this is the center of Earth, so you have that Earth's radius, capital R, and now the mass is located somewhere above the surface having an altitude equal to small h. In that case, if you apply the same equation, that F will be equal to gme into m divided by r plus small h square, right? Because now the distance between both masses, the Earth itself and that object, is r plus h, right? We can again write that F is equal to mg and cancel out that m, and g will be equal to capital G me over r plus h in this case, r plus h whole square actually in this case. So now let's call that g, which is the acceleration due to gravity for an object or experienced by an object located somewhere above the surface, let's represent it with g sub h. So there I added a subscript h in that particular gravity, acceleration gravity. And what I can do here is that I can write gme equal to g naught time r square from this expression, and then put that gme into that expression, this one, right? And I can write finally that g at a particular height is equal to g naught r square over r plus h whole square, right? So I have written the value of g at a particular height in terms of the value of g at surface. And the value at surface we can exactly determine from this expression. I can also write that as gh equal to g naught multiplied by r over r plus h whole square. So r plus h whole square can be considered as a modifier which will modify the value of gravity at surface to get you the value of gravity at any height, right? And that modifier is a function of two things, the radius of Earth, which is constant, and the height of that object from the surface, right? So everyone is clear how I came up with that expression at the bottom? Any doubts or any questions? All clear? So let's plot that expression now and see how the gravity varies when a particular object is raised from the surface. We know its value at surface is 9.8 something, and I will exactly tell you up to several significant figures. But now let's plot that expression on the bottom right to see how the value of gravity varies when an object is raised from the surface up to a certain height like 10 kilometers, 20 kilometers, and so on. So the same information is here. So g naught is the value of gravity acceleration at surface and more specifically at the sea level, right? So now we have that expression at the bottom. Let's plot it. Obviously, for plotting purpose, we need to first calculate g naught, which we can determine using that expression, using the radius of Earth, mass of Earth, and the value of capital G. It will come out to be this number in SI system and this number in the US system. The capital R or radius of Earth is 6371 kilometer or 3959 in miles if you are using US system. Mile is also a unit for distance in US system. So if I plot that equation, this one, so let's have g sub h on y-axis and the height of a particular object from the surface on x-axis, right? Because capital R is constant, g naught is constant, so we can plot it on a graph. That graph will look like this. So here I have g sub h on y-axis, the value of gravity at a particular height versus that height on x-axis, right? So small h is on x-axis and I plotted it such that h is in kilometers, right? So now you can imagine or you can see from actually here or observe how the gravitational acceleration reduce as you go away from the surface of Earth, right? Uh, Here you have like 1000 kilometer, 2, 3, 4, 5000 kilometer, and then slightly more than 5000. Actually, this particular point is equal to the radius of Earth, capital R. So the value of g is reduced to almost 1/4 of its value if you are raised from the surface to a distance equal to the radius of Earth, right? So g naught is a value 9.2 here, and it reduced to 1/4 of its value at a distance equal to the radius of Earth, right? This gives you a rough idea of how the gravity reduces. Now, what is the height of International Space Station which is rotating about Earth? Any guesses? Yes, please. 400 kilometers. So on that x-axis, now see where that 400 lies. Somewhere very close to this point, right? And at that particular value, the value of gravitational acceleration is almost same as 9.81 or 2, very close to the value of gravitational acceleration at surface, right? But we also know that the astronauts on the International Space Station, they are weightless. They are in a state of so-called 0g. But here you have an equation which you plotted and you saw exactly mathematically that they should have almost the same weight as on the surface of Earth, right? So why they are weightless then? Is it because the gravitational acceleration is very less there? You have seen that it is not less, right? So please guesses. It is in a state of free fall all the time, right? So when you are in a state of free fall, you feel weightless, right? So International Space Station is revolving around Earth with a very high velocity, and due to very high velocity, the Earth's curvature is not letting it going down and sink into the Earth's gravity, right? So it is revolving around Earth and it is in a constant state of free fall, right? And free fall is a state which you will feel as a weightless person, right? So imagine that you are in a closed container which is in a free fall state. You will feel weightless up till the time that container is in a free fall state, right? So International Space Station is constantly in a free fall state, and therefore the astronauts feel like they are weightless. So your distance needs to be very large in order to have a significant difference in the gravitational acceleration. So they feel weightless not because the value of g reduce at 400 kilometer, but because they are in a free fall state. So the value of gravitational acceleration will be very close to what you will have on surface at that distance, at that height actually. So actually mathematically, if you see, that line will never go to zero. There will never be a distance or an altitude for which you will have exactly 0g. It will keep on reducing with more and more distance. So theoretically, you will never be able to get out of Earth's gravity no matter how far you go from the surface, right? But the value will keep on reducing like that. Sometimes when you plot things in which one of the axes is increasing or decreasing exponentially, very high number, then you can sometimes make one of the axes or both of the axes logarithmic, which means, for example, here what I did on x-axis, I plotted the same equation such that each unit increase is now 10 times increase in the values, right? So now from 1 to 10, 10 to 100, 100 to 1000, and so on. So you can see that up till first 1000 kilometers of altitude, the value is close to 9 or slightly above 9 meter per second square, right? And then once you go more than 1000, 2000, 4000, then the value reduced to a lower number. So this gives you a physical idea or intuition about how the gravity varies with altitude. So when you are dealing with calculations related to the application of law of gravity close to Earth's surface or close to the orbits, low Earth orbit or high Earth orbit, please keep that range in mind roughly so that you can develop a feel or can check your calculations with your intuition also. So there is nothing like 0g at these distances where we generally think. The second is the effect of rotation of Earth, and let's just quickly discuss that, and we will end here. We'll solve some problem maybe next session, but in between you will be having a tutorial also, so you will already be using that gravitational law in different forms. But let me just quickly state the effect of rotation, and we can catch that up from the next session onwards. Earth is rotating about its own axis, and we are also rotating. That rotation actually affects our weight, right? Compared to if it was a stationary globe, right? And that is the effect which we need to account in the gravitational acceleration. So it's not that we are on a fixed globe, but we are rotating. That effect actually, what is your idea? And let's end on that thing. The effect of rotation should reduce our weight or increase our weight. If Earth was a stationary globe, would our weight would be more, or if it is rotating about its axis, it would be more?